Fluids in motion or hydrodynamics, that is what we're discussing today. And we'll look at what happens when a particle of fluid is in motion, what are the various forms of energy involved, and then we analyze an application to that. So as usual, we'll start by looking at the various forms of energy. So first, what you see there is that when you're talking about a particle of fluid that's in motion, there are three energies that are involved. There's kinetic energy because it's flowing. There's also potential energy because of some height, and then there's also pressure energy. So considering these, we can break them down one by one. For potential energy per unit weight, of course, this is the energy due to some height above a given height, above a given point or datum. If you refer back to the formula for potential energy, it's mgh. So here, we avoid using h, we're going to use letter z to represent the height. Then mg is weight. It represents the weight. So combining them, you'll notice that here, m and g can now be replaced. Weight is like that. But since we are saying per unit weight, it means weight is 1 Newton. So the whole of this, even when you substitute for this, it is taken up by a number which is 1. So our potential energy per unit weight is at Z, or the height. This is in joules per Newton, joules per unit weight. Kinetic energy refers to the energy possessed by a particle of fluid because of its motion or because it is moving. So formula is half mv squared. So again, if I look at this m, mass is the same as weight divided by g because weight is mg like we saw there. So if you make mass the subject, what you have is weight over g. And remember that weight is 1 Newton. So if you substitute back in this expression, you have v squared over 2g because the g is still here. So this is what represents the kinetic energy per unit weight. Pressure energy per unit weight, this one is given by pressure over specific weight, pressure over specific weight. So in this case, we're saying pressure divided by that specific weight, which can be density times gravity. The same unit again, joules per Newton. Now here comes Bernoulli's theorem. In Bernoulli's theorem, we're saying that the total energy a body of fluid or a particle of fluid possesses remains the same. It remains constant unless maybe you have a leakage or some energy is allowed to enter the system at some point. So mathematically, that's how you write it. Now, if you have to write the equation the way things happen in practice, because this is the ideal equation, but the practical equation of Bernoulli's, Bernoulli's equation written in that way has to take care of the losses. So the first part, in the section 1, we have velocity, or the energy as a result of that velocity, which is kinetic energy, v1 squared over 2g plus p1 over omega plus z1 being equal to this now, v2 squared over 2g plus p2 over omega plus again z2 plus the losses. Here you may have the total energy that entered in, but before you get to section 2, you may experience a number of losses in between. And as we go in this subject, there's a point where we're just going to talk about the losses in pipe flow. When fluids are flowing in pipes, what are some losses that are involved? So there, where we're saying losses, we expand them to categorize them and specify what those losses are. Are they due to friction? Are they due to bending of the pipe and so forth? So come back to that very soon as we go in the subject. Then apart from that, the counterpart to Bernoulli's equation is what we know, what is known as the discharge or the rate of flow. The rate of flow follows the continuity of flow principle, where when you look at this, we say multiply the area by the velocity. It gives you the amount of volume flowing per unit time. The volume flowing per unit time. So that is our discharge in cubic meters per second. But how the continuity principle comes in, because as long as, look at this, for example, if I have this section and then suddenly I have that going to a smaller section like that, well, here there's a transition between the two. So what happens now is that when it is flowing like that, the amount flowing per second remains the same. If here I have 2 liters per second, even in this smaller section, I should have 2 liters per second, because the volume that is being allowed from the source per unit time is the same. The only thing that is going to compensate for that change in cross-section is the velocity. Here where we have a cross-section which is big, it will flow fast. I mean, here with a big cross-section, the flow will be slow, the velocity will be slow. But as it comes here now to where the section is smaller, it's going to flow very fast, because here, when the velocity rises, it means the cross-section area is smaller, and vice versa. Here, where the area is very big, the velocity at which the liquid is flowing is small. But what is constant is the rate at which this liquid is flowing, or the discharge. That is what you get there. Now, we also have coefficients. Coefficient of discharge. We include this coefficient whenever we're trying to calculate the actual discharge. Now, apart from that, we also have the coefficient of velocity, CV, and the coefficient of contraction. The coefficient of velocity refers to when you multiply this CV by the theoretical velocity, you get the actual. Even the coefficient of contraction of that body of fluid flowing is the same thing. So for a coefficient of discharge, when you want to get the actual discharge, you just cross multiply coefficient of discharge times the theoretical discharge, the theoretical one that you've been given. So that is how you get there. We'll again expand this when we come to discuss the Venturimeter. Coefficient of contraction, we're saying this is the area between the area of a jet. We're referring to a jet, something that may come to mind easily. Here is a tank with an opening on the side. Then because the level of liquid is up to here, you find that as water comes, it will produce a jet at a certain speed, and water will continue flowing like that. Now, what happens is that as it comes out, it tries to narrow out a bit, then it reaches its narrowest end somewhere, then it continues down there. There's there where we call the vena contractor, because it will try to contract when it comes from there, and then after that, it is free to continue moving like that. So the ratio between the area of the jet or stream at the vena contractor, meaning where it contracts, to the diameter of the jet. The diameter of the jet is normally supposed to be given by the diameter of the opening there. So that's why we're saying coefficient of contraction, area of the jet over area orifice. actual theoretical. That's how they stand side by side. CV, coefficient of velocity, refers to the ratio between the actual velocity and the theoretical velocity. Now comes what we call laminar flow. Here we're saying that here you have individual particles that are arranged in an orderly manner as water comes out, individual fluid lines. That's laminar flow. In turbulent flow, the particles do not come out in an orderly manner. They can be zigzag or disorganized. That's why it's turbulent. So they do not follow specific paths or follow specific patterns, not at all. Laminar flow is the one where you have orderly arrangement of fluid particles as they come out of the orifice or the opening, or as the liquid is flowing. Now, having discussed that, let's look at some applications of fluid dynamics or Bernoulli's equation. Now we try to apply this. So here we have been given a pipe which is carrying oil, specific gravity 0.9. Then we're told the diameter is reducing from 300 going all the way to 100 along the direction of flow. And this pipe is actually horizontal. Rate of flow, 400 liters per second. And the pressure in the smaller section is 100 kilopascals. Now, let's find the velocity of the oil in each section and also the pressure of oil in the large section. First things first, let's arrange our data. What we have is the specific gravity, 0.9. So if it's 0.9, to convert it to specific weight, we have to multiply by the specific weight of the pure water. So 0.9 by 9810, you get 8829. 0.9 by 9810, you get 8829. Then area 1, which is referring to this bigger section, we say pi d squared over 4. So pi times 0.3 squared over 4. And we get this. Next is area 2, pi times 0.1 squared over 4. And we get 7.854 times 10 power negative 3. Next, we have the discharge. This one has been given in liters per second. You need 1,000 liters to make 1 cubic meter. So as we try to convert, we just have to divide this 400 by 1,000 and we get our value in cubic meters per second. The second is okay because this is our SI unit. So 0.4 cubic meters per second, 400 divided by 1,000. And then the pipeline, the nature of the pipeline is that it's actually horizontal. So you're dealing with a pipeline which is coming out like that, horizontal, horizontal. Then you have the bigger section going all the way to a smaller section there. Oh, sorry. This is even a pipe. All right, then smaller section comes there. So what you have is that this side here, this is your 300, and the other side there, that is your 100 millimeters. So what we have, if you look at the center of this pipeline, if you look at the center, it's the same. There's no difference in height between section 1 and section 2, meaning potential energy cancels out because height number 1 is equal to height number 2. Z1 is equal to Z2. It's 0. So that's the smartest way, the simplest way of analyzing it to make your analysis faster and easier. Then we've also been taught, because for now, we are saying that this is our section 1. That's what we and this is the section 2, the smaller one. So if that is the case, then what we've been given, according to the question, we've been told the pressure in the smaller section of the pipe is 100 kilopascals. In other words, pressure 2, because this is for section 2, P2 is 100,000 pascals, 100,000 newtons per square meter. We've just converted this 100 kilopascals to what we have here. Next one, we have the discharge now. Here we're trying to find now the velocities, velocity 1 and velocity 2. We go back to the continuity equation, this formula for discharge. One thing we said is that A1 V1 is equal to A2 V2 because the rate of flow remains constant. The discharge remains constant. So meaning that this is equal to the same. The same is also equal to A1, A2 V2. So we are here. Q is equal to A1 V1. Q is equal to A1 V1, referring to the discharge. So from there, you can just make the discharge, V1 the subject. So you can now have V1 is equal to discharge divided by the area. So there we have it, 0.4 divided by the area that we had. And this is our velocity number 1. As usual, area 1 was bigger. 300 millimeters diameter was quite big compared to area 2, which was using 100 millimeter diameter. So if you look at this one, we're saying Q is also equal to A2 V2. They're making Q V2 the subject, picking it from here, we're saying 0.4 over the area, which is 7.854 by 10 power negative 3. When you divide them, you get 50.929 meters per second. This is the smaller section, and the fluid is flowing faster because the section is small. Here, the fluid is sluggish. It's moving slowly because the section is wide. It's quite large compared to the section 2. Now, the question was asking us to find the pressure in the larger section, referring to P1, this one here. So again, we go ahead and write Bernoulli's equation in full. V1 squared over 2G plus P1 over omega plus Z1 equals V2 squared over 2G plus P2 over omega plus Z2. Let's do the substitution. V1 is 5.659 squared over 2 times 9.81 plus P1 over, this is 829, then plus 0, equals, then you have this 50.929 squared over 2 times 9.81 plus 100,000 over 8829, then everything plus 0. Now here, remember where we have Z1 and Z2, we had said these are actually zeros from the data because the pipeline is horizontal. So once you do that, make P1 the subject of the formula. What you find is the answer we have down here, which is 1.252 meganewtons per square meter, or 1,252,803.65 newtons per square meter. That is our final answer. Now, that was horizontal. What if the pipe is vertical? Now, the way this happens is that a vertical pipeline of diameter this uniformly tapers upwards to 120 millimeters and is conveying air whose density is this. And the speed of air in the larger section is 20. Then the pressure in the large section is 5 kilopascals. Then what we have is it says the larger section of the pipe is under a pressure of that and is 3 meters below the smaller section. Determine the pressure of the air in the smaller section. All right, now, what you see is that when you read this question, you come up with this diagram here. This diagram, you sketch it from scratch because it's not going to be given. But if you're able to visualize without sketching, which is usually a bit tricky, you can go ahead and do that. The idea is to make sure that you don't get it wrong, especially with Z. So what you've been told is that this large section is 3 meters below the smaller section, meaning that the distance from the last section to where the small section is going upwards is 3 meters. With that in mind, let's try to put the data together. First thing, area number 1, referring to where we are coming from, the large section. This is our 1. This is section 1. Then we are going there, that's our section number 2. Now, the naming of these sections is not something you need to worry about because they can even be the other way around. The idea is that if you say this is your section 1, this is section 2, make sure all the parameters belonging there are taken care of according to the way you've called it. If you call this as section A, this other one as section B, again, maintain it like that, because when you switch them, then you start creating confusions. So area 1, because the formula we're using is pi d squared over 4, so that's pi times, this is 240. The 240, if you convert it to meters from millimeters, you divide it by 1000, you get 0.24. So pi times 0.24 squared over 4, you get 0.1885. Next is area 2. Area 2 is coming from this one, which is 120 millimeters. And 120 millimeters means that we first have to convert it by dividing this by 1000. So 120 divided by 1000, you get 0.12. 0.12. Now with that, we still go back and say pi times 0.12 squared over 4. Again, that's the answer for your smaller section. Then comes specific weight. We've been given the density in kg per cubic meter. So with this density, we need to convert it to newtons per cubic meter. So all we do now is omega equals 1.2 times 9.81. What does it give us? 11.772 newtons per cubic meter. That is our omega. So we have the specific weight for the air. Then let's pick up the velocity. We've been told that velocity in the bigger section, the velocity in section 1, the velocity in the larger section, this one has been provided as the 20 meters per second. So that's why we're saying our V1 is 20 meters per second. At the same time, we also taught that the pressure is 5 kilopascals, which is 5,000 pascals. Now, the other one is Z. This is below the other one. To get the 3, we measured this height from here, representing that this is our Z1. Where the larger section is, that's our Z1, representing 0. Then Z2. Z2 is this one here. Because this is the height from there up to where this smaller section is. So Z1 is 0, Z2 3 meters. Then let's apply the discharge formula. A1 V1 is equal to A2 V2. Why are we using this formula? Because we were already given the velocity in this large section, but the velocity in the smaller section was missing. So making V2 the subject, you have A1 V1 over A2. A1 V1 over A2. So our A1 was this. Our V1 was 20. Divide that by A2, which is this one. So the answer we get is 333.333 meters per second. 333.333 meters per second. Remember, to get this velocity, it's just here. Just use this and we made V2 the subject. And there we are. Now, the question is saying determine pressure of air in the smaller section. So since we have all the parameters we need, we have all the values we need, we go back and plug Bernoulli's equation. Bernoulli's equation, V1 squared over 2G plus P1 over omega plus Z1 is equal to V2 squared over 2G plus P2 over omega plus Z2. V1 was 20 squared over 2 times 9.81. Then P1 was already provided as 5,000 divided by the specific weight of this air, which from the data was 11.772. V2, we just found it to be 333.333. 333.333. Divide everything by 2 times 9.81 once again, plus P2 over the specific weight, and again plus 3, because Z2 is 3, Z1 was 0. With all that, the number simplified to this, 445.1245, that, and then P2 over 11.772. And it comes to P2 over 11.772. Finally, our P2 has to carry it a negative here, just like that, because this other number we're having here is already having a negative. So negative 61,461.85 pascals. For pressure, this is very normal. And in fluid flow, sometimes we say it has created a vacuum. But anyway, negative pressure is the opposite of positive pressure. So that is very normal. There's nothing wrong with having pressure which is negative. It's just telling us how the fluid flow is behaving. Here we have now a Venturimeter. So we thought that this Venturimeter is installed in a pipeline whose diameter is 100 millimeters. All they want is to determine the discharge. Specific gravity of that oil flowing in the pipe, 0.8. Specific gravity of the mercury, 13.3. Then the torque of the diameters, there is 80 and 25, both in millimeters. So then, specific gravity is 0.8 for the pipe. Then specific gravity for the fluid in the manometer rather, where we are trying to test, is 13.6. X is the difference in height in the mercury level, because what we've been told here is that the difference in height of mercury between the entry is 80 and the throat diameter is that. Oh, sorry, it's the. Here we have a scenario where we use a YouTube manometer. I think here it was not mentioned, but either way we'll connect it this other way around. So what happens here is that you have this pipe, and then you interrupt it, have a venturi in the middle. This is where the pipe section comes to a smaller size. So there we connect and we connect. So after that interruption, things get back to where they were, meaning the pipe section is allowed to regain its original diameter. But there's an interruption in between to allow for fitting of this small throat. See the throat section or the venturi. Now what happens in here is that between the two, between the inlet, section 1, and the throat, you connect a YouTube manometer there. Now, what you're going to discover is that this YouTube manometer behaves a bit interesting. You're going to see a difference in mercury level here, there. That's how it will behave. In this YouTube manometer connected between the two sections, the intensity of pressure will cause this difference in height. So the difference in height being referred to as X is this one here. And that's the one you label as X. That is our X being referred to. Then, so that is the difference in mercury level between the height, the inlet and entry. That's the 80 millimeters. Provided 80 millimeters, now we have to convert it. It's our 0.08 because we divide by 1,000 as usual. Coefficient of discharge, 0.96. Then throat diameter is 25 millimeters, which is 0.025. Then section 2, which is the throat here, section number 2 is there, 0.025. So all we will do is we can decide to get the areas, but deliberately, this is our section 1, whose diameter is 100 millimeters. Convert it becomes 0.1. So with this area 1, you can find diameter 1. You can be able to find area 1, which is pi d squared over 4. So what you have now is pi times 0.1 squared over 4. Multiply that, you get 7.854 by 10 power negative 3. Then the fluid flowing in the pipe is 0.8. So 0.8 times 9810, you get 7848. Then we also have the area ratio between this inlet and the throat, which is A1 over D1. So basically, it's like pi d squared over 4 pi d squared. The pi over 4 cancels out from the formula there. What you remain with is D1 squared over D2 squared. So A1, the ratio between A1 and A2 is the same as the ratio between D1 squared and D2 squared. So we can just bring the two diameters together. Even if you go ahead and calculate the areas, plant them there, you are still going to find the same area ratio, 16. So the area ratio, that is the ratio between the inlet and the throat section, the ratio between the area of the inlet and the area at the throat section or at the constriction. Now, with this in mind, we can now get to this part. So the difference in pressure head, H, is given by, you have X outside, then specific gravity of the liquid in the manometer divided by the specific gravity of the liquid flowing in the pipe, minus 1. Either this or P1 minus P2 over omega. Of course, we do not have these two. Both of them, either of them, both of them are supposed to give you that H. So after that, you can now substitute. Your X is 0.08. S1 is 13.6. The other one is just 0.8. Everything take away 1. So your height therefore becomes 1.28 meters. Now let's get back to the other formula. Here we're talking about the difference in pressure head. Now the difference in pressure is what we could be looking for. So we come to this formula, H is equal to P1 minus P2 over omega. So we can just cross multiply because we want P1 minus P2. So the omega we're using is the omega for the fluid flowing in the pipe. So P1 minus P2 is equal to that height multiplied by omega, height multiplied by the specific weight. So 1.28 times 7848. 1.28 times 7,848. And our answer is 10.04 kilopascals, 10,045.44 newtons per square meter. The other part is talking about us finding the actual discharge. There are so many formulas for the discharge, but here we have either we can use this formula on top or we can use this one below. This one we've written here, its simplified version is this one right here on top. If you look at the way we arranged our data, we already made way for us to use this formula. CD, area 1, which is the area at the inlet, then square root of 2gh over m squared minus 1, everything in the brackets. Now, with all that, you can now say that, let's do the substitution into there. Our CD, coefficient of discharge was 0.96. Area 1 was 7.854 by 10 power negative 3. The square root of 2 times 9.81 times the h was 1.28. Then area ratio, the m, was actually 16. So 16 squared minus 1. So once you do all that, the answer you get is 2.36 times 2.366 times 10 power negative 3. This is our actual discharge. The theoretical discharge, we were not going to include this one. This is our actual discharge, just as the question had requested us to find. So yeah, the actual discharge, pressure difference. So those are the ones we've just finished calculating. And as usual, take your time to go through the exercise. The exercise here has 6 questions. I try to plant the answers there so that as you practice, you can gauge your progress. Thank you, thank you, thank you. We'll meet in the next lesson. As usual, post your comments, reach out if you feel there's an area that needs to be sorted out somewhere.